This is 6.2.3, molecular kinetic theory. Now, the molecular kinetic theory is a simple model to explain how gas molecules exert pressure on the walls of a container Now, important point here, which is a common misconception, is that the gas molecules don't exert pressure because they collide with each other. So pressure is not exerted due to particle collisions. It is due to particle wall collisions. So in fact, we're even assuming that particle collisions don't really happen between each other. They only collide with the walls. So we assume particles do not affect each other. Now, the kinetic theory model has 4 assumptions. So these are: 1, time occupied by collisions is negligible compared to the time in between collisions. So during the collision itself, while a particle changes momentum, the amount of time that takes is very, very small compared to the time it takes for a particle to fly between 2 different walls of a container. Number 2 is that the volume occupied by gas particles or gas molecules is negligible compared to the volume occupied by the entire gas. Which is the volume of the container. Number 3 are that all collisions are elastic. So energy is not lost. Number 4, forces are negligible except during collisions. Now, we'll put a box around all of these statements because these are things you need to learn. And then we'll do a quick qualitative analysis on why pressure is exerted on the container. So first of all, when particles collide with a wall, they change direction. If they change direction, that means that there is a change of momentum. If there is change of momentum, then there is also rate of change of momentum. If momentum has changed, then that means that the velocity of the particle has changed. So according to Newton 1, a body remains at rest or constant velocity unless acted upon by a resultant external force. So in this case, if velocity has changed, that means there was a force. And according to Newton's second law, force is the rate of change of momentum. So there is a force on particle because velocity changed, and that comes from Newton 1. And the force is equal to rate of change of momentum which comes from Newton 2. Now, Newton 3 then says that every action has an equal but opposite reaction, which means that there has to be the same type of force but acting on two different bodies in opposite directions. So if there is a force on the particle during that collision, then there's also a force on the wall of the container. So there is equal but opposite force on the container. That comes from Newton 3. And then pressure is force over area. So force per unit area. Now we'll begin the derivation mathematically, which is actually a derivation that you need to be able to do. So on a new page, we do the kinetic theory derivation. So we construct a two-dimensional image first of a container, and we imagine a particle, gas particle, bouncing between the two walls. So the particle may go from there to there with some velocity, and then it might bounce on that wall and come back again with another velocity. So we'll label the velocity going to the right as u, and we'll label the velocity going to the left as minus u. So when there is an elastic collision, the momentum change of this particle becomes minus 2 mu. Now, if there is a change of momentum, and it takes some finite amount of time for that momentum to change, then the force is given by the rate of change of momentum. Now in this case, I'm going to drop that negative sign because I only care about the magnitude of the force. I don't care about the direction. And the direction changes depending on which wall it's bouncing off of. So we're going to do the force is equal to 2mu all over delta t. Now, that's the force of one molecule. The force of all molecules hitting the wall would be n times that amount. So F total is equal to 2n mu all over delta t. And then we can say that there's a certain amount of time it takes for the particles traveling from one wall to strike the next wall and then come back again to strike the same wall again. So time for particle to collide with the same wall so in order to do this, we have to think about the distance that it travels. So if that distance is defined as s, then for a particle to strike one wall, strike the second wall and come back again, it does a distance of 2s. So we use s equals to ut, but we use 2s. So 2s equals to ut, therefore t equals to 2s over u. And then we can substitute that back into the above equation. Which was 2nmu all over 2s, and then we put u on top, so it becomes squared. Now the 2's will cancel out, so that's nmu squared over s. And then pressure is force over area. So if we take that nmu squared over s and we divide it by area, we get nmu squared over sa. Now, if container is a cube, where all sides are x, then a is equal to x squared and s is equal to x. So therefore, at the bottom here, we've got pressure equals to nmu squared over x cubed, and x cubed is the volume of our container, which gives us P equals to nmu squared over V, which gives us PV equals to nmu squared. Now, this entire time, we've assumed our molecule to be moving in one direction. So now what we want to do is we want to make it move in all three dimensions. So molecule velocity has 3 components. So if we imagine the molecule living on an axis, where we've got the I, J, and K directions, or the X, Y, and Z directions, if its velocity is represented by some vector arrow, and we call that C, then that vector arrow has some X component, some Y component, and some Z component in 3 dimensions. So C squared is equal to U of X squared plus U of Y squared plus U of Z squared. We assume it moves in all directions equally. So the easiest way to do that is to just say that all 3 components are equal. So assume all 3 are equal. And that gives us C squared equals to 3 times U of X squared. In this case, we can just get rid of the X because it doesn't matter at this point. So 3 U squared. And so that means that U squared is equal to 1/3 C squared. Now if we substitute that back into our equation from above for pressure, we had P equals to NMU squared, or PV equals to NMU squared. And then we can make the substitution there for C squared. So we've got 1/3 NMC squared. Now, if we also want, we can divide the V across. So we keep one formula here, PV equals to 1/3 NMC squared. And if we divide the volume across to the other side, then you've got 1/3 NMC squared over V, but mass over volume is density. So we also get that pressure equals to 1/3 N rho C squared, where rho is the density of the gas. Now, one thing I forgot to do here is that N times M would be the total mass of the gas, because we're doing the total volume of the gas rather than the volume of one molecule. So that N should also disappear, because NM over V squared, over V, to get this equation. Okay, starting a new page, we'll start wrapping up. So let's write down first the kinetic energy formula, EK equals to 1/2 mv squared. Now, for a molecule of CRMS speed, which is a root mean square speed, a molecule with speed CRMS, we can sub that into this equation to get EK equals to 1/2 m CRMS squared. And then we also know that PV equals to 1/3 NM CRMS squared from the previous page. Now for a single molecule, n is equal to 1. So we get PV equals to 1/3 MC RMS squared. That means that free PV equals to MC RMS squared. And then using this, we can start to make some substitutions. So, for example, the MC RMS squared, we can make a substitution there. So we'll get EK equals to 3 PV times by half. So that's 3/2 PV. And PV is also equal to NKT. So therefore, we can make the substitution here. For one molecule, N is equal to 1. So we can get rid of that N. So PV equals to KT. So here we also get EK equals to 3/2 KT. And KT also equals to R/NA. So we get a third equation, which is 3/2 RT/NA. And that's the end of 6.2.3.